Hey there everybody and welcome back to another Blender tutorial. In this one, I'm going to be showing you how to make a smoke simulator all in a single tutorial. It's going to be particle based using geometry node, simulation node dynamics, and nobody's done this on the internet, so I'm going to be the first. This video is brought to you by Squarespace, but we are going to talk about that later. I have an emitter object. That can be a sphere, whatever. Here you can see the smoke that's being generated. It is intentionally low resolution at the moment. We can up-res it, but you can see it collides with objects even as they're moving. And we have control over a lot of stuff. So as you can see, this is actually what's going on behind the scenes. It's doing a point simulation, converting that into a volume which we can up-res and also control parameters of. So I'll keep this brief. Here's boring smoke that just rises. We could easily add turbulence to this, which you will see kind of appear in a second. So now you can see the stream isn't perfectly straight. I can also add vorticity. Vorticity is what makes the smoke kind of curl and do all these interesting things. And I can increase the particle count, which is what's going to make the smoke not look so like a bunch of dots. But yeah, that's what we're going to be doing. Smoke simulator. There's other things like buoyancy, diffusion, cooling. Let me get into it. So, smoke. How do we even start something like this? Smoke is basically a very simple idea, even though it looks complicated. What it is it is a substance. We're going to make it out of particles that rise. Clearly, they kind of float and rise until the temperature of it gets cold enough that they don't, okay? So there's some kind of fuel source, some kind of heat source, like a candle, a fire, whatever. That makes these smoke particles hot. They rise, and as they rise, they cool down, and then they kind of fizzle out and start dropping. That's literally all we need to simulate. There's some, like, extra things with that, but whatever. So what I'm going to do is I'm going to add a smoke object. I'm going to make that a geometry nodes object, so just add your geonodes modifier. And this is entirely for smoke, so I don't need my group input. And I'm going to make a emitter. This can be anything you want. I'm just going to have a really smooth sphere, okay? So I'm going to call this emitter. Step one is we need the emitter, whatever object that is, to generate particles and kind of shoot them outwards from the surface. Then, of course, we're going to make them float and stuff like that. So with the smoke, what I want to do is I want to import in this object. Which object? The emitter. And by the way, you want to set this to relative. The reason is, so let's say I move the emitter over here. I'm going to hide it. And I'm going to show the emitter. You can see it kind of moved it back to the center, even though we imported in the data. You want to set it to relative, is what I was trying to say, because then it will actually follow the geometry relative to the origin. Doesn't matter. Okay, so here we have our emitter, and I want to make a bunch of points. So I'm going to distribute points on faces. The thing is, when I play this, that's all there is to it. We have points. They don't update. They don't float. And more importantly, we don't get more points over time, right? I'd have to increase the density. What I want is for every frame, it's going to generate more and more points. So clearly, we need to distribute points on surface, but over time using a simulation zone. Okay? So all I'm going to do for this difference is I'm going to take our simulation zone, again, that feeds in an input, and it cycles, and every frame it does a repetition. Every single frame, I'm going to join, I'm going to add new particles that we've created, okay? So the way I want you to think about this is we start off with an input of nothing. There's nothing there. And then on the first iteration, we add some points, okay? This gets fed into the output, which goes back to the beginning, which now has some points. Then we add more and more and more. So now when we play this, this isn't exactly what we want, but you can see we indeed have our points. And when I look at the point data, so here you can see we already have 2,500 particles, even though it doesn't look like it. It increases as we play. The reason that you can't see these new particles is these particles are being spawned in the exact same spot. So there's actually 42 particles overlapping right here because we're on frame 42. So I want these to generate, but at a different position each time. So take your seed and connect that to the frame number. So every frame, it's going to give us a different random seed to generate points at different places. And let me save this. By the way, of course, main file is going to be on Patreon, so with all the settings. So now you can see we have a point generator. That's literally all you need to do to make a point generator. If you bring down the density, it's going to do it more slowly. If you bring it up, it's going to do it faster, whatever. But I want these points to spawn with a velocity with movement that shoots outwards relative to the normal of the emitter. Okay, easy enough. What I'm going to do is our particle spawn, and then I'm going to give them an attribute, so they're born, and then right out of the gate, well, I guess we could do this here. Right out of the gate, we are going to give them a velocity, so they're born, and then we're creating an attribute that stores the normal. Okay, so points are distributed, and then it will reference the normal of where it spawns from. Okay, kind of weird. Point is, as I play this now, if we look at this information, we have a velocity channel that we can actually use by setting position, right? I'm going to move the points now using this velocity. So I'm going to call this velocity, connect that here. This is probably going to go pretty quickly, but you can now see that particles are shooting outwards, and we've made a emitter, okay? What's happening is every single frame, we get our new points that now have their velocity. That is the normal of the surface, the direction pointing outwards, and then every frame it's offset by this velocity. So clearly this is too much. So I'm just going to very easily scale this effect down. So if it's at 100%, let's put it at 20%, and now we have an emitter that's not as intense. And that just works, okay? So, as I mentioned earlier, this video is sponsored by Squarespace. My website, www.cgmatter.com, is made with Squarespace. I just drag around blocks to design this website, which right now I'm using to basically promote a product. You get analytics, which are important for that, so you know who is going to your website. And additionally, you get an asset library, so I don't have to re-upload and worry about where my files are. And I also happen to be using it for some affiliate marketing because it can do forms and stuff like that. So, head over to Squarespace and design your website, make it amazing, and when you're ready to take that thing live, you can use my link in the description to save 10% off your first purchase of a website or domain. Now, one thing I want to mention is everything I've been doing, and I want to do this now because it's going to get complicated if I don't explain this. Everything we've been doing is at 24 FPS, okay? Fine. If I play it, it looks like this. Get that in your memory. It's going at about this speed. However, if I now simulate at 60 frames per second as if I want more detail, you can see they're shooting out actually faster. It's not like the video's smoother, they're actually shooting out faster. And the reason for this is on every simulation step, we do this offsetting, but there are more simulation steps if there's 60 frames per second, we're moving more frequently, so obviously it's going to be faster. To fix for this, we have this delta time. Delta time is equal to 1 over the FPS, so it could be 1 over 24 or 1 over 60, and the higher the frame rate, the smaller this is. So I'm actually going to scale this by delta time, which you're going to see barely moves it, right? But now, so kind of focus on what this looks like. When I change the frame rate, yes, it's going to be smoother, but it's actually going at the exact same speed. And that's because the amount we're moving it updates relative to the frame rate. Now, if we want them to just kind of go faster for whatever frame rate we use, but it's going to be at the same speed, now we can just multiply it by something like 4. Okay, so it goes like this, 60 FPS, same thing, but smoother. Okay, so I just want to emphasize that because anytime we do any kind of update, we're going to want that to be relative to a DT or a delta time. Okay, so at this point, we've actually already done a lot of the work here. So this you can think of as updating the position with velocity. I'm going to hit Control G to make this a node group, and I'm going to call this position update. okay? Because in this section, we're updating the position. In fact, we can also do something here, Control G, and we can call this our spawner. So very simply, we get our input points from here, we spawn more, we update their position. But even though they're emitting in all this, we now have this issue where they don't care about gravity and buoyancy and everything like this. And additionally, they kind of like propagate outwards infinitely, which is kind of a weird kind of look. So to add gravity, what I want to do is I want to have a velocity going upwards. Gravity is downwards. Forgot. We want to make a velocity that goes downwards, because now we're saying particles fall, but that velocity gets bigger over time, like objects speed up as they fall. And that's because of Newton's second law that says that forces, like the force due to gravity, is kind of like on an acceleration basis. It doesn't change the position, but it changes the velocity, which is what acceleration is. What I'm saying is that we're also going to need to have an acceleration, or in other words, a force, something acting on it, in this case, gravity. So I'm going to make a vector. This is going to be our force vector. And what the force vector is going to do is it's just going to store, for now, negative 9.8. Okay? So on every single frame, I'm not using any delta time or anything. On every single frame, we have a gravity of negative 9.8. You could simplify to just negative 10, I guess. This is the number you'll learn in physics. It's gravity acceleration on Earth. And this force should change the velocity on every single frame. So remember, when we spawned it, we gave it a velocity. And after we create a force, we now want to say our velocity, which is whatever it was before, is now also affected by the force. So let me, easier to show. I'm going to take my velocity and I'm going to add a contribution of the force. Okay, simple expression. And this is going to overwrite the velocity. So again, we're spawning points that have an initial velocity relative to the normal. Then we're saying every single point, I don't care where or when you are, you're going to be subject to gravity. And then your velocity is going to be what it was. But then we also add this gravity, which in this case is negative. Okay, so these are probably going to fall pretty quickly. Boom. They fall quickly, but you can tell that there's some kind of gravity going on here. Of course, this seems to be a little too strong. A little too strong. So what I'm going to do is I'm going to take the force, and I'm going to say, well, first thing we need to do is remember, every time we add a contribution, the frame rate's going to be an issue. We want to say take the force and scale it by delta time. So if we go at 60 FPS, it doesn't add force super quickly. And actually, that seems to be pretty good for gravity right off the bat. Along the same lines, yeah, so we have our delta T basically affecting our position update. Another thing I want to include here that isn't here is no, that's fine. Forget what I was saying. What I was trying to get at is delta time is important, so I want to make sure that the position update is also influenced by it, but it is. However, I don't like that we're multiplying by 4, because this will make it will make our velocity always 4 times bigger, whereas I just wanted to make the normal a bit stronger, so a bit of a technicality. I'm just going to go back to the spawner. And do what I was trying to do, which is taking the normal and making it 4 times larger. So in this case, we're giving it a bigger normal instead of saying make the velocity 4 times bigger, which isn't necessarily true because I want gravity and stuff like this. Okay, so now you can see it explodes more like a fountain. If I make this number smaller, it doesn't. If I make it 0, it just falls. Okay, I'm going to keep it at 1.5, so it's kind of subtle. Okay. But you can see very quickly we've implemented forces, which is in this case only gravity, etc., etc. Okay, so this I can also make a node group with Control G, and this is going to be not our position update, but our velocity update. Okay, And believe it or not, we're actually pretty close to getting smoke. In fact, this is smoke if it didn't float, just falling smoke. The thing that is going to make this more smoke-like now is we just need to play with the forces, right? Gravity is overpowering, so it goes down. But imagine I set this to a positive number. Now it kind of floats upwards, which is more like smoke. Of course, we have more work to do with this, but you can see what I'm going for. So what is the force, right? We have a force of gravity. What is the force that pushes the smoke up? Because clearly there's something doing that. Well, imagine we have a smoke particle. Gravity's pushing it downwards. The thing that's pushing it upwards is a force of buoyancy. You might know about things floating in water. They're buoyant. They rise to the top. Same thing with smoke. They're like more buoyant than air, or less dense or whatever. In other words, we have gravity here, and here we're going to have buoyancy. So we need to calculate buoyancy and add them together. And when buoyancy is bigger than gravity, it goes up, and then otherwise down, and when they're equal, they're suspended. Okay. What is buoyancy? Well, we know that buoyancy is basically a vector that goes upwards. So I'm going to use 0, 0, 1 to point up on the z-axis. But the question is, how strong should that be, right? So we have that vector. I could now kind of set this up properly. So I'm going to, on our first input, have -10. That's our gravity. And now I'm adding this buoyancy. Okay, so this is still going to fall, but not as quickly. And as our buoyancy gets bigger, so now gravity is equal to buoyancy, they're both 10. They just kind of suspend, there's no acceleration. I make this bigger, and now they suddenly ascend. But again, the question is, how do we know how big this buoyancy is? Well, before that, I realized this normal is still way too strong. Okay. How do we know what this should equal to? Well, the thing about buoyancy is the smoke rises, but only when it's very, very hot. When it's hot, it kind of pushes the air out of the way. So the smoke is very hot here, and that makes it rise. But as it gets higher and higher and higher, it cools down because it's not near the heat source, and that means that it becomes less buoyant, and then it starts falling. So again, there's kind of like a fire source here that makes it very hot, that makes it very buoyant, that makes it rise. But as it goes further and further up, it's cooling down, which means it's getting less and less buoyant until it's at equilibrium, and then it goes back down. In other words, what I'm saying is we need a temperature attribute. Yeah. So in the spawner, I don't want to just initialize a velocity, but I want to give it a temperature. And we could be super, in the same way that I just made gravity 10, I don't need to say temperature is like 73 Kelvin or whatever. I'm just going to set the temperature to 1. And generally, we're going to be dealing with temperatures between 0 and 1, just to keep it simple. So we have a temperature of 1. And now I want to scale our buoyancy by this attribute. So we should have temperature right here. And now it's not going to rise, but now it's using this. Remember, temperature maxes out at 1. So I can multiply this by like a buoyancy factor. Let's say it's 20. And then on average, it's going to go up, right? At least when the temperature is 1. However, we also need the temperature to now decrease over time. An easy way to do that isn't necessarily accurate is we can say that we should have a temperature update. So I'm going to say I want to overwrite the temperature attribute. It should be initially set to itself. Okay, so I'm taking the temperature, and on every single frame, I'm going to, I guess I could subtract a little. That isn't necessarily correct, because what I'm saying is if every frame you lose 0.1 degrees, like, shouldn't cooling kind of like slow down and stuff like that? We might get into that, but for now, let's kind of go with the simple case and see what we get. So on every frame, the temperature is going to lose some amount. Again, this is something that depends on our frame rate, so we're going to do delta time. Let's see what this does. Okay, so you can kind of tell. It rises and then it falls, right? And this is kind of like a extreme example. So what I can do is I can have this temperature cool down, but not as quickly. So I'm going to divide this by 4, so it cools down 4 times slower. So it rises and it speeds up until at a certain point it's cooled, and now it's falling, okay? And all of these are numbers that you want to expose to the user so they can control the cooling rate and all of this. So really, if you're not doing it linearly, right, you're asking how should the temperature go down? The temperature should go down relative to how hot it is compared to the ambient temperature. I know that's weird. So imagine the world here, everything around the smoke has a temperature of 0, okay? And the smoke can have a maximum temperature of 1. When it's 1, it's very different from the ambient temperature, so it's going to drop very quickly. However, as it gets very close to 0, like now it's 0.1, and it's almost the ambient temperature, it slows down how much it's cooling. So it's not necessarily linear. That's not really how it happens. The way it actually happens is in a non-linear way. To keep it simple, imagine the world around this, so not the smoke, but everything around it has some ambient temperature, some temperature that the room is in. It's like room temperature. And let's say, for keeping the math simple, our temperature is 0, okay? The smoke starts off at a temperature of 1, or at least a maximum of 1, which means it's very different from 0, right? So our minimum temperature is 0, our maximum is 1. They're the biggest difference they're going to be. It cools down very quickly. However, as this plays out, and now let's say the temperature is 0.5, as it cools, it's much closer to the ambient temperature, so it's going to slow down because it's not so far away, right? It keeps cooling, and now the temperature is like 0.1, 10% of what it was before, and it slows down even more. So it's kind of this like non-linear thing. Just so you know how to model this differently if you wanted to, you could take the temperature and multiply it by some number that's like less than 1. So if it's 0.9, it's going to lose 10% of temperature every frame. But that's going to be extremely quick, as you can see. So you want to make it like 0.99. So it does this, and it's going to max out, and boom. Okay, so that is something you can do. Again, you're going to need it to be relative to delta T. But I'm not going to do that. I'm going to have a linear temperature fall off to keep this simple. Okay, so really, we just implemented buoyancy. So it now floats until it doesn't. Now, normally you don't see smoke falling, right? Because once it's cooled down that much, you don't see it anymore. So exactly at the point where it starts falling, it's basically invisible. And we can simulate that by saying, so notice that some of these temperatures, once it gets very, very up there, become negative, right? Because we keep subtracting. What we can say is when the temperature goes below room temperature, it's negative. In this case, we can say just delete them, okay? And this will make our simulation faster. So delete any points where the temperature is less than 0, which is also good because we don't like negative temperatures. It doesn't really make sense. So now it rises, and it's going to start to fall, and then it deletes them. Perfect, okay? So already this is a little more smoke-like, I guess. I'm going to make this its own node group. This is going to be our deletion. So notice how we're turning every block into something quite simple. This is going to be our cooling because we're subtracting temperature. And for force, I'm going to keep this exposed right now in case we want to change it. We have our deletion, but another thing that's going to make this look more, I don't know, like it's getting less strong is we can also, I wanted to play it longer so I can talk as this happens, so I can keep simulating. Also, what we can have happen is these smoke particles, and you can think of their size as almost their temperature, perhaps. We can have them get smaller. So we have big particles, and then they get tiny, tiny, tiny until they're basically invisible. The cool thing about that is we are storing the temperature on every single frame. So as the temperature becomes 0, it should be invisible, but we want the radius to be 0. So you can see, if I make the radius the temperature, we get that for free. And you can do that outside the simulation zone because we're already calculating for this. So I'm going to set, not position, but I'm going to set point radius. So this lets me make my points bigger or smaller, so you can see how you can make a smoke plume here. I'm going to make this equal to our temperature, which is a attribute. So I'm looking for temperature. I'm going to connect that here. And while this is ridiculous, you can see that these points start off big, and as they go up, they get smaller and smaller and smaller, which gives the impression of them kind of disappearing. And to get the size that I want, I'm just going to divide by like 5 or maybe 6 so that they don't start off as big. Now, nothing says that this should be disappearing in a linear fashion, right? Like I could totally, remember this is between 0 and 1. I could totally make my own custom function, especially if you know physics, you might know what to do. I could do something like this or something like this, and you can see how it changes kind of the visible fall off. So this is linear, this is not. And again, this tiny modification makes it look more like smoke. So at this point, what is preventing this from looking like smoke is that it's just going perfectly upwards and there's no like turbulence or like any interesting kinds of dynamics. And we're also actually missing diffusion and stuff like that. But it is working. I can increase the normal and kind of get like a bigger, you can almost think of it as pressure, or you could have it be negative and kind of like do this little pine cone thing. Up to you. By the way, I guess what I just saw is that we should not have a radius less than 0. So I'm going to divide this. Or sorry, I'm going to clamp this so that when it's less than 0, it just stays at 0. Again, we need dynamics and maybe we also need diffusion. Okay, new topic. Another thing that makes smoke is not just its buoyancy, but since smoke particles are kind of like these tiny things in the air, no density essentially, they basically don't collide with each other. That isn't actually true, but for our frame of reference, we don't need to really care about collisions. We don't need to check when two particles are colliding and then say, this one goes this way, this one goes that way. Instead, there are so many particles and they're all like overlapping and kind of going through each other that there's this thing called like Brownian motion. And I know I'm kind of bringing this out of nowhere, but instead of doing particle to particle collisions like you would do with fluids, what you assume here is that they're always touching each other and moving in random directions. That is called diffusion, and that is something that makes it look like smoke. So another thing I want to include here is on every single frame, the velocity should just be nudging a little in a random direction. Like a particle gets it, oh, now it's going slightly down, now it's going slightly up. And it can be pretty chaotic as well, but on average, it's going to kind of disperse, right? If you put smoke in a room, it expands. Okay, and do you see what I'm getting at? And we don't need to be super fancy with this. We can actually just take our velocity function, and at the very end, we can add a random direction, right? So this is going to be my random vector that can go all the way to the left, all the way to the right, up, down, whatever. And for the seed, I want to make it different every frame. Now, by default, this is going to make it look crazy, but you can see that now on average, it's expanding, right? It's expanding because we're saying that there's collisions all the time and there's this Brownian motion, whatever. But clearly it's too strong and there are some things to correct for. So first of all, just because every direction is possible with this random value, it doesn't mean each one has the same magnitude, right? What I want is we have a point and there's a sphere around it where I can choose, I'm going to go this direction in the sphere or this direction. What the random value does is it actually makes a 3D cube going from -1 to 1 on each axis, where if I pick this direction, it's not going to have the same magnitude as this diagonal, which is longer. The point I'm making here is you want to make sure you normalize this. Normalize it. So after it picks a direction, it's going to make it the same magnitude, and then it goes there. So it's going to look pretty similar, but that's just a caveat. And then also, it's too strong. So just like all the other kinds of things where we're scaling, I'm going to scale, but not just by some random number I want. This is, again, something that should be controlled by delta time, because otherwise diffusion happens more often at 60 FPS. We don't really want that. So I'm going to do it by dt. Let's see what that looks like. So you can't really see the diffusion because dt is so tiny, which is fine, because now it's frame rate invariant, so I can just multiply it by some number. Like, let's say diffusion should be 5 times stronger, and now you can see it expands. So let me turn off diffusion, and now you can see it's this perfect pillar. Let me turn on diffusion, and now it's doing a bit of expansion. Okay, so now we have a diffusion thing. Next thing, very important, is turbulence. Turbulence. What that basically means is that things don't necessarily, we're not in a vacuum or in a perfect situation where there's just gravity and buoyancy and then temperature cools and things happen. Usually you simulate this thing, or you have smoke in the real world where maybe there's wind or gusts or even just micro turbulences where one part of the room's hotter than another. That is going to introduce noise. We call it turbulence, and there's a lot of ways to do turbulence. So you could think of turbulence as basically saying we run the simulation, and after each step we can say look at the position of a point and just kind of move it somewhere else randomly to say, oh, there was wind here. That's one way to look at it. Another way to look at it is kind of like as a velocity thing. So if a point's over here, it can inherit a velocity that says go that way. Okay? So instead of moving the position, I'm moving the rate of change of position. I'm moving the velocity. Yet another way to think about this is if you think of it as actually a force, like something like wind, then it should be over here at forces, which change the velocity, which change whatever. I guess if you're thinking of it as wind, what would be physically accurate is a force. That doesn't mean we have to do it for our simulation, but for our source of randomness, I'm not just going to use a random value, because even though it's random, there's kind of a consistency or a smoothness to the wind. It's not different at every single point. There's some kind of consistency. So I'm going to use a noise texture instead, 3-dimensional output. I always say this on this channel, but noise texture, which is this 3-dimensional thing, goes between 0 and 1 on X, Y, and Z in this kind of smooth way, which is great, but I also want it to be able to go in the negative direction. So not just some random number between 0 and 1, but it could go negative or positive, which is why I always subtract by 0.5. So instead of 0 to 1, it's negative 0.5 to 0.5. Connect that here, and let's just see what this does. Let's see what this does. Okay, it's not very clear if this is visible, so I'm going to scale it by, let's say, 10 times. I'm going to scale it by 100 times. Okay, and now you can see the turbulence is taking place. So we're just adding some randomness that, of course, we're going to figure out what the correct numbers are to make this look the best. But I guess this actually doesn't need to be... I'm trying to think if this should or shouldn't be subject to delta time. I don't think it should, because forces are kind of this, like, ubiquitous thing. They're everywhere, and the time step only matters for when we're updating the velocity or the position. So I'm actually just not going to do it. And now let's look for some good numbers. So let's say I have a turbulence of 25. Okay, so it's not just the strength of the turbulence, it's also the quality of it. So for this part, I'm actually going to spawn many more points. So every frame we're spawning a density of 50 points. And the reason I'm doing that is I want to see how my turbulence affects. Also, just for this, I'm going to turn down my Brownian motion, my diffusion. Okay. So I'm going to play around with these numbers until I get something that kind of looks like you can kind of make it out. So let's see. There you go. Okay, so clearly this ain't it, but you can see that there's kind of this force that goes that way. To me, this says that it's too small, so something like that. And by the way, notice how it kind of comes out in kind of this wavy way, which is exactly what I want. So let's see. Okay, We don't really get to see the simulation for too long because the cooling's happening too quickly. So let's have the cooling happen at 20% rate, so divide by 5. Okay, that looks pretty good. That looks pretty good. The reason it's making this cone shape, by the way, is because it's shooting out from the sphere off its normals, which even a tiny contribution can add up over time. So if I decrease that, it shouldn't be as big. But definitely part of it is diffusion for sure. So very soon I should expose some of these parameters so that we can actually play with them. Okay, so we have a bit of turbulence. If I make that stronger, you'll see it's really spreading out. I think the reason that we're getting this, like, on average giant cone thing is, yes, there is turbulence, but it's the same over time. So let's say there's a little pocket here where the noise is saying add a force in this direction. Every particle that enters this pocket will have that influence, right? It doesn't change over time, whereas the wind isn't always going this way. Sometimes it chops and goes in different directions. So what I'm saying is that this noise texture, to make it more accurate, should be animating over time. That's what W does. So if I change this over time, and this is where it's going to get a little messy, here we go. Now you see that actually did it. That actually was the secret. You can almost see there's some form to this now. You want the noise to change over time, as if the wind is, like, not perfectly stationary. Okay? So you can see that did something. As I decrease the scale, there's going to be bigger average motions. So that looks pretty good. If I make it 0.1, it's just going to look like there's one big thing. So this could be good for when, like, a candle gets extinguished. It kind of looks like that, like one kind of stream. I'm going to go for a number here. Okay, and really, because we're simulating, the magic of this is just playing around with numbers and seeing what works. So for the scale, remember, if I make this tinier, we're going to have less turbulence. 50 looked very good. Let's see what it looks like when it's super windy. Yeah. So maybe if it's a super windy day, you could do something like that. I like this. Now, at this point, we're starting to get pretty messy. So let's actually show you how I would set this up as a simulator. I would look at every important number. Like this 40 is the scale or the magnitude of the turbulence. So hit N to open this menu, and then I can call this turbulence strength. And now, the idea is, what is the idea? Now it's in the simulation zone. I actually don't want that. The idea is I want the user to be able to easily change this over time. So I'm going to add a group input, this time connected to the 40, so now it shows up here. And then we can call this turbulence strength, which should be between 0 and, let's say, 100. And then the user can pick it right here. So I play the simulation, it's 40. All of a sudden, I turn off the turbulence, it becomes flat. Increase the turbulence by a lot, and then it does that. So nice user input. Let's quickly pick some numbers that we want the user to care about. So this is going to be turbulence scale, which doesn't get bigger than 0, doesn't get bigger than 5. You can just make this up as you go. Buoyancy, remember this is the strength of our temperature force in a sense. So that's actually super important. Buoyancy between 0 and 100. I don't know why I keep writing 199. So let's actually show you buoyancy. So it starts off floating. I kill the buoyancy, and all of a sudden it's going to kind of like, you saw how it just kind of turned into a dust. Pretty interesting. And when I make this big, the smoke rises super quickly. And that, again, the hotter the thing is, like if you have a forest fire, it goes much faster because of that temperature. Anything else that is important? Yes, I think, yeah, this is our Brownian motion, our diffusion, our dissipation. I don't know if you could call it that, but that's pretty important. So I'm going to call this diffusion, which can go between 0 and 10. Again, with these 9s, 0 and 10, that's all I care about here. And then for the cooling, for sure, I want to control how fast it cools, which is kind of like an inverse relationship in this case. The bigger the number, the slower it cools. So to just kind of get around that without doing some extra manipulation, I'm going to call this coolness slowness. Or you could, or like, let's see, the bigger the number, the longer the animation is going to live for, in a sense, each particle. So instead of that, we want to call this lifetime. That's actually an interesting way to describe it. And then for our other things, I mean, you could call this when the size is less than 0.1 or something, but I'm pretty happy with that. I guess the only other thing is kind of this particle size that we can decide after the fact. Okay. Let's make that a parameter. So this is going to be our, I mean, I guess it's going to be our inverse size. So the bigger it is, the smaller the dots. So I'm going to call this detail or something like that. Doesn't really make sense. So as I increase the detail, I mean, it kind of looks like detail. So now that we have this, let me show you how to actually make it look like smoke. Not just, by the way, it already kind of looks like smoke if you just kind of look at these particles. But I mean how to turn this into an actual volume. Before I do that, I just want to pick numbers that I like here. So let's say that this is our simulation for now. We have our points in 3D that are basically guiding this. How do I turn it into a volume? It's actually super simple. After you do this set point radius, literally just run a points to volume. Boom. And now it's a volume. Important thing is we recalculated the radius, which it's just ignoring here. So as I make the radius smaller, you can see it becomes more finely detailed. You want to use this new radius we made. So connect that here. It's not showing because these points are so tiny and our volume is so low resolution. So you can take the voxel amount and just bump that up. And the more you bump it up, the more detailed this is going to be. Okay? So doing a particle only pass makes it quite quick. Okay, so we have our radius here. You can bring up the density to see it more. This doesn't really seem to be the way, so maybe what I can do is I can now play with my detail. Like that. So I'm saying the points should be a bit bigger if we're doing this volume thing. And hopefully in that case, we can bring down the voxel amount some. Just like in normal simulations, the bigger the smoke is, the more volume it occupies, the longer it's going to take to compute. Because here you can see the bounding box. Because, you know, there's more stuff we need to turn into smoke. So by the way, if you don't want, you're going to see the bounding box of this goes quite high. If you don't want to waste compute on particles you don't even see, this is why the deletion group matters, where I can now say anything that's colder than 0.1 degrees, don't even show it. And by the way, this turning to volume thing can be done after the fact. The simulation's just for points. So I can just take a frame here, expose it, bring down the detail. And you know, I'm not really drawing too much attention to it, but we've like pretty much made a smoke simulator. The hardest thing to implement that mine has that I don't think I'll do here is vorticity. What vorticity is it makes the smoke kind of curly in a way. And I'll just explain the theory of how we might do that in a future tutorial if people email me and want to. You basically generate a bunch of points. These can be random, or they can be based on how hot the area is. And these points are areas of swirling. So maybe one swirls the other direction. And you basically look at a smoke particle and you say, which swirl am I closest to? In this case, this one. So start revolving. Okay, so there's basically like a bunch of revolves that happen in places is the way I would calculate vorticity. But maybe as a final note, and another thing that I'm not going to implement here is as I move this, you're going to see it make smoke and then it rises, but it doesn't have any like momentum, right? I go like this, and there's also no sub-stepping. It just doesn't really make sense. Like if I go like this, smoke should kind of shoot out. And that's difficult to do with also substepping, but we'll get back to that maybe. What I do want to implement maybe before we wrap up here is let's do a collider. And what I mean by a collider is a object that the smoke has to wrap around. That'd be cool. So for this, I'm going to make it a wire, just so we can see it. Doesn't change any of its properties. I want the smoke to say, oh, I'm here, I gotta go around, okay? So let's think about how to do that. So imagine, how do we know if a particle needs to go around it, first of all? So imagine you have all these particles, okay? Let's specifically look at this one. This particle is inside the sphere, which means it didn't collide with it. Ideally, what we want is this smoke particle to have wrapped around it. But what happened for the smoke particle to get in here where it's not allowed? Well, initially, it was somewhere outside of here, and it's rising and maybe going this way until it's inside the sphere. In that case, the way we correct for this is we say, okay, if you're inside the sphere, pick the place that is the closest to exit. So if I was to pick this point of the sphere, I could move the point such that now it's come out of the sphere, so I'm resolving a collision. I'm saying if something's inside the sphere, move it to the nearest point where it is no longer there. But that's not necessarily enough, because if my trajectory was like this to get inside of here, and now we're saying, okay, map it over here, so now it's outside of the sphere, what's going to happen on the next frame is, again, it's going to try to go this way, and it's always going to be inside. Which is fine, but if we want to clean this up a little, what I want to do is I also want to change its trajectory. So let me just draw one final diagram. If we have a point coming in like this, not only do I want to bring it outside of the sphere, but I now want to modify its trajectory so that it goes outwards, which means we're going to change the position and the velocity, is what I'm getting at. So we are going to do that right after the position update. So basically we have our forces, our velocities, and that ultimately changes the position of the smoke particles. But then some of those positions are going to be inside the sphere, which is now why we're correcting for it after the fact. So I'm going to import in our, I'm going to call this, if it lets me select it, I'm going to call this our collider. How do you spell collider? I feel like it's not two L's. Maybe it is two L's. Okay, so we have our collider. So let's bring in our collider. Again, set it to relative. I want to know what, first of all, I guess I want to know, is a point inside the sphere, okay? To do that, imagine we have a point right here. A trick to know that if it's inside or outside the sphere or any object is you look at the nearest point, and we know that relative to this point, our smoke is inside the sphere, but there's not really a good way to tell that. So what you do is you look at the nearest point, and at that point, you look which direction is like outwards facing, like which direction is the normal, okay? So you first of all have this vector, which is saying which direction is the closest exit. Additionally, you have a vector saying which direction is the surface going outwards. If those two things align, so in this case, you see these two arrows are pointing the same way, it's inside. Whereas, if I have a point over here and its nearest neighbor is right here, it's now pointing into the sphere, but the direction of the normal is the other way. So only when these two vectors line up is what I'm trying to say. So that's how you do it in the business. So I need to know the nearest point. So I'm going to do nearest. There's a couple ways to do this. I like sample nearest surface. So I sample the nearest part of the sphere. What I want to know is what is the position of it. So again, I'm looking at the nearest neighbor and getting that position. I want to know the vector. Remember, if it's in here and it's going here, I want to know this vector, which is our nearest exit minus where it was before. So that's how you point out that vector. And additionally, I want to know the direction of the normal, which we can do, again, very easily. If find the nearest surface point, and evaluate the normal. We might want to evaluate this on a face, so we'll see what we can do there. But I want to know if these two are aligned, and you might already know this if you took some math. The way to do that is the dot product. I'm not going to explain the math of it, but all you need to know is if you have two vectors and you want to know the angle between them, in other words, do they align? There's this operation called the dot product, which will give a number close to 1 when they're aligned, and a number close to -1 when they're pointing in opposite directions, and a number of 0 when they're like perpendicular to each other. So not quite aligning, not quite not aligning. In other words, I want to look at the dot product and check where it is greater than 0, which means they align, which means that it's inside. Okay? So now we know our point's inside. Under that condition, I want to move the point outside of the sphere, so I'm going to set position to that nearest surface point. Again, I'm only going to do this under this condition. So only if the things align and it's inside, then I want to move it to the nearest surface. And we could start there. Let's just see what that looks like before we continue. Again, the reason it's so slow is this volume step. And just for our visual clarity, I'm going to make these smaller. So let's see. It goes like this. And now, a little hard to see in 2D, but now you can see it's actually reflecting here. It's a little hard to tell, but it is wrapping around it. Maybe it is easier from this direction. So we have this, and additionally, I can move it and update it live and kind of push. This is like most of the battle. If you wanted to, like I said, so kind of the issue here is if I have like a cube and rotate it a little, let's see what it does with that. So it's going to collide with this surface. It goes here. You see it really struggles, so it does get cut off, but you see it really struggles to kind of wrap around it, like a little of it makes it. It really struggles with that, and that's because we didn't do our velocity update where it now updates our trajectory. And we talked about how to do that. So we have our position update, and then we want to do our velocity update, which I will keep simple. All we're going to do, again, this isn't using continuous collision detection or any of this. You want to update the velocity. So let's set it equal to itself. We want to update the velocity, but, so let's say a particle went in here from here, and now we're resolving it by bringing it outside. Now the trajectory should be the opposite direction. The way you describe that mathematically is you look at the surface normal, the way out, and then you just say, take this vector and flip it relative to this vector. So again, if you have a surface, you have a collision, you just bounce it off relative to this normal line. And that's called a reflection. Luckily, there is an operation for this. So all you do is you do reflect. So we're going to take the velocity and reflect it off of the surface normal, which we already have. Again, it's not clear to me if it does faces or not. So let's see if this does anything different. By the way, this is not going to work at the moment. Let's see if you know why. Whoa, it's doing weird stuff. Can you figure out why? The reason why, but by the way, you're seeing it is kind of sliding on a surface as if it was on this cube. So that might give you a hint. Basically, it's doing this velocity reflection thing all the time, not just when we had a collision, right, which is when we care about. So all you want to do is you can't just connect this here, by the way. Not necessarily. It might do some weird stuff. Interesting. You want to make sure that it was a collision beforehand. So let me show you what I mean by that. I'm going to capture this, which is telling me, was it a collision before we resolved it, before we moved it out of bounds? So we wanted to know, was it originally a collision? That's why we're capturing it. And under that condition, reflect the velocity. Won't necessarily give something different, but you can see now at least it's trying to do something. Clearly, a big issue we have here is it reflects like way too strongly. Like it just is like a mirror. So we can make this a little weaker by saying lose 50% of your velocity on collision. So let's just see what that looks like. So now it's going to collide, but it doesn't necessarily go like infinitely far. And I want to boost up the lifetime. Oh, by the way, one very obvious parameter I forgot is in our spawner, I want to control the density, of course, for how many particles. And I care about that right now so that we can lower it to actually see what's going on here. Okay, here we go. So you can see they're bouncing and they're working their way around the surface. It looks a little weird because they look like actual bouncy balls, so you really want to kill the velocity here. Maybe it only keeps other way. Maybe it only keeps 10% and it gets rid of 90. So maybe that's a bit much, but you can see it's starting to kind of crawl up this surface. So let's try 0.2. Almost. It seems like they're getting quite stuck here. Maybe 0.4. And there might be something else we can do to actually get these to wrap around. So that seems to be one thing. I think another issue might be when we have a particle colliding and we bring it to the surface. It's exactly on the surface, right? It's not like an inch away. It's exactly on it. So if we give it a bit of buffer room, that might help as well. So something to consider. If we wanted to give it buffer room, we already have the direction of the normal that we can offset by. So this is going to be ridiculous, but just look at this and boom. You see there's kind of like this line over here where they spawn further away. That's great, but of course it is too strong. So I'm going to scale by, let's say, 10% maybe. And that helps it get around. I just don't want it to be visible. I also want to get rid of this annotation. Found it. So hopefully at this point, I can turn down the scale of the reflection. And do notice, this is kind of a hard boundary to work around. It's pretty steep. It does work procedurally. So maybe one way to think about this is it would actually require quite a long lifetime to get around this. So you could just do this. You see they're slowly getting around. Clearly there's a bit of work we can do on our collisions here to make it easier. Just another idea. If you wanted to increase the chance that it makes it out of there, what you do is you wouldn't only reflect off the normal, but you'd also give it a bit of a randomization after the fact so that it has, like it doesn't perfectly bounce off the surface the same every time, but you instead give it a random push, so you could add a random vector. For now, I'm not going to deal with that because this is way better than what we had before. So let's see, it rises and then boom. It can work its way around the surface quite nicely. So we have colliders, and you could turn this into a collection instead of an object. So here's a good example where a bit of curvature helps it actually work its way around, which looks really cool. Let's bring down the lifetime. These should not be living this long. Maybe a lifetime of 7. I forget what the number we used was. That looks a little better. Maybe a lifetime of 10. So, again, anything you do here, we're doing a particle simulation, and only at the very end here are we kind of like wrapping a smoke on it. Where, again, in this case, we have this like detail thing. Is this correct, or do I want the opposite? Very confusing how I set this up. But you then put smoke on top of this. And this is something that, because it's just volume, will work both in Eevee quite quickly and in cycles if you want it to look better. And I haven't even gotten into fire or anything like this. You can do that. Let me know. Let's see. And you can also control the density of the smoke in some sense. You don't want to bring it too high, otherwise you can really tell. Okay, so final things. I could do a part 2 if people are interested. Final thing is I want to take everything we did here and just turn it into one kind of situation. Control G. So this is going to be our collision. It's important to do this, by the way, not just for visual clarity, but especially when you're sub-stepping if you want to. Very important. What is all this for? This is our force. Let's also wrap that into one thing. So now we're getting quite clean here. Make all of this level. Bring that here, here. I wanted to add 1 or 2 more details that we can do for free and just add a bit of believability. You want to add just tiny bits of randomness wherever you can. One place we can do that is we do our cooling, not our cooling, we do our spawning, where our temperature is always spawning at 1. Doesn't need to be the case. You can have a temperature where some of them start at 80% as much. Okay, so we now have a basic smoke solver that does pretty much everything that I would want it to do except for like sub-steps and vorticity. And it works with collision objects. It wraps around them. You could also kind of do something that's kind of like a collision object, and what it really is a kind of like a bounding box, where you could say, you know, the simulation's inside this box and you can collide with these walls and everything, but that contains it to a certain size. Or you can say when you exit that area, instead of a collision, just delete the particle, like an open boundary. But there you go. Again, I just want to emphasize the turning it into a volume step can be done at the very end here. So there you go. I hope you enjoyed that tutorial. If you want the full version that I made and you can play around with, you know, some different techniques that I did, you can check that out on Patreon. Or if you just like what I do and want to support it, Patreon is the best way to do that. So I want to thank all my beautiful, amazing, better than normal, the normal non-patrons, patrons. You also get early access to tutorials. Either way, thanks for watching.